Hello everybody and welcome. You're about to see a tutorial about the Coriolis design flow, which is aimed at making ASIC. In order to correctly use the design flow and parameterize Coriolis, you will first need an introduction about the steps involved in making an ASIC. So the presentation will be organized as follows. First, I will make a short introduction about what is it to make an ASIC. Then, present the two main steps of the making an ASIC, which are the placement and the routing. Then, I will go to the full design flow and present the reference of the free tools I use. And finally, I will end up with the demonstration itself. So, what is making an ASIC about? Basically, an ASIC is just a drawing. This is this drawing that you send to the foundry being the ASIC factory. But it is not just any drawing. It is a very complex one that must follow lots of complicated rules, we call them design rules, so that the factory can really fabricate it. In our terminology, this drawing is called a layout. Now, this is the most basic diagram for the design flow. It is a V-cycle, meaning that the left-hand side of the diagram breaks things down into elements of the standard cell library, and the right-hand side did reassemble them in a complete layout. The entry point of the flow is a RTL description, register transfer logic, which you should be already familiar with, at least I hope most of you, because it's what you feed to an FPGA compiler. So it's the same description, exactly the same. But we apply it a different treatment. What we do is logical synthesis on the left hand, which breaks the logical equation into logic gates, which are 1-bit elements, like for example the NAND2 gate, which is represented in the blue background, and which have a layout equivalent. The basic idea is to break things down into elements that have a layout equivalent. Once we have done this step of breaking things down, we reassemble the whole thing under the shape of a layout using the place and route steps. And what you get in the end is either a symbolic layout, this is the AP file, or a real layout, this is a GDS2 file. We will see in the next slide what is the difference between a symbolic file and a real layout. As I just said before, Coriolis supports two kinds of layout, the symbolic layout and the real or physical one. I will start by a brief history of the symbolic layout. The symbolic layout was invented in the 1980s by Mead and Conway based on the observation that whenever you change of foundry or technology, what you mostly do is a shrink. So instead of drawing one standard cell library per technological node or foundry, they decided to create an anonymous unit which is called the lambda, and to draw their standard cell once and for all with that unit. Then, when they wanted to target a given node, they just have to make a shrink, like it is shown in the right part of the slide. It is slightly more complex than a shrink because you also add a small delta on the wire width and a small delta on the extension of the segment. But it is mostly a shrink. This technique is very successful, but it has the drawback that you cannot achieve the same density than with the real layout. It is at the start of the Moses service in the US. One other advantage that was unforeseen at the time is its independence toward NDA. One of the limitations when you work in a real layout is that you have to sign an NDA, which prevents you to share your design, to share the layout of your design, which can be problematic in terms of security when a third party wants to see or check that the layout is really what it is meant to be, or some kind of audit or other thing, and it's come increasingly as a concern. So, Coriolis can support both. So, now I will talk about the goals of Coriolis. The first goal is to provide a platform which is suited to academics to allow them to make algorithmic on any experiment which may need to modify the database or any internal components, which is something you cannot achieve with commercial software because you cannot tailor it to your exact needs, and you may be prevented to publish your results due to NDA agreements. And lastly, you may have backward compatibility problems. It has already happened that an academic bases work on a certain version of a tool, and then the next version breaks things. So it's quite painful. The second point is to build a free and open source community. By freeing the layout and freeing the code, we hope that people can start to share their layout and create a community. Third, we want to open the markets, the ASIC market, to the SMEs. Because there has been a drop in price of the mature technologies. Now, making a chip in an old technology is affordable for a small company or small enterprise. But the cost of the software tools or the EDA tools are still very high. The license fees are very high, so it prevents them to use it. So by providing something free, we hope to help them. Another trend that has arisen recently is the question about security. You want to ensure that your chip has not been modified to include some kind of Trojan or other malware. You want to be able to check that your chip is actually what it was meant to be. So having free tools for that is a plus. And lastly, we may have some problem with long-term maintenance. For example, nuclear power plants want to have the same component for a lifespan of 50 years. So imagine a chip or any design that lasts 50 years, and it's quite complicated. By making everything open, we hope that people can ensure the continuity of their design. So now we will narrow the focus of this presentation, the use of Coriolis as a silicon compiler. But to understand the error that can occur, you must be able to orient yourself in the design flow and to understand what is possible and what is not. To illustrate that, I will present a representative example of a small design. The complete design flow is made of a collection of various tools. This collection may seem a little bit complex at first glance, but it is the result of history. At first, there was the Alliance toolchain, which was complete with logical synthesis, physical synthesis, verification tool, and timing analysis. But it was limited to symbolic layout and can only manage up to 10,000 kilogates. So, by the start of the year 2000, we developed the new Coriolis part, which is a re-implementation, but only of the physical synthesis. And this one can handle at least up to 500,000 kilogates, assuming that it is the upper limit because I didn't get my hands on bigger designs. So, the toolchain is an assembly of various parts, which are first the tools coming from Alliance, because we didn't suppress all the tools. Some of the tools, especially in the verification and the translation between netlist format, for example, between VHDL and Verilog, are still used. Then there is, of course, the Coriolis physical design steps, but also IOSIS, which you should know for the logical synthesis, because it's the same tool that you use for FPGAs. And finally, the Alliance Check toolkit, which provide a set of scripts to automate the making of ASICs and a set of examples. This is on those sets that we will work later. So the three parts came from Lipsys, and of course IOSIS is not hosted by Lipsys. Now, let's have a look at the placement. On the left side of the slide, you see the netlist expressed as a schematic. That is, you see the signal like A and B, connecting gates expressed as logical Boolean function. On the right side, you see the equivalent in terms of layout. Each gate is replaced by its equivalent layout, and what we want to do is place all the layout of the gates inside the designated area without any overlap, and with respect to some optimization criterion like the total wire length of the design, that is, the total sum of the wire lengths of each net. But there are also other criteria. In this presentation, I will not talk about the algorithm involved in the process. I only talk about the problem to solve so you understand which are the parameters at play. As I said, the placement of the standard cells must be done without any overlap. But it goes beyond that. As you can see, the cells are organized in rows, which are also called slices. The consequence is that each standard cell must have the same height as the other. It has also a pitched width, that is a width which is a multiple of 5 lambda. Here. You can also notice that the power lines are shared, which means that every one row over 2 must be flipped vertically. This is the sense of the arrow you see there, here in normal orientation and here in flipped orientation. There are also blank space that remains because of the algorithm, which needs at least some free space, and for other reasons that we need to sometimes insert extra components like polarization contact to avoid the latch-up effect or diodes to avoid antenna effects. After having looked at the standard cells, now let's look at the metal layer. Metal layer will be used to build the wires that will connect the standard cells. The metal layers are stacked on top of each other and numbered from the substrate, meaning that metal 1 is the closest to the substrate and metal 5 the farthest. There are also cuts between the metal layer. The first one is called a contact, meaning that a contact is a cut between the substrate in green and the first metal layer, the metal 1. Other cuts, like this one, and this one, and this one, are in fact vias. A via connect two metal layers. The metal layers are then organized in preferential routing directions that you can see on the right side. The metal 1, for example, is in the vertical direction, then the metal 2 in its perpendicular, that is horizontal, then metal 3 vertical again, and metal 4 horizontal again. So this is crisscrossing the design. This is called Manhattan routing for those who may not know already. The routing tracks are regularly spaced. The router must be able to put a via at any point in the track without generating any DRC violation. To ensure that, we compute the minimal distance of two tracks, for which this condition is always verified. For example, here, the minimum side of a via is 3 lambda. Then the minimum distance of metal 2 side by side is 2 lambda. This yields to a 5 lambda pitch. The pitch is the distance axis to axis between two neighboring tracks, and it will ensure that the routing is DRC clean by construction. Now we put the two of them together. That is the standard cell layout at the bottom and overlaid the routing tracks. This is called over-the-cell routing, in which the routing area is overlaid upon the standard cell area. This also means that the number of wires that you can pass over a certain area is limited. So this is also another reason why you may have to expand your placement area. It is because there is not enough space to make the routing. And that is highly dependent on the kind of design you are making. Some designs do not require a lot of wire and can be placed without a low spacing factor, but others may need a bigger one. Now, if we try to solve the routing problem head-on, it will not work because the sheer amount of data is too big. So we must abstract even more our problem. we do so by introducing the concept of G-cell. A G-cell, as shown here on the bottom left of the figure, is an area of, for example, 10 by 10 tracks, which is abstracted into one point. Then we rebuild a routing grid which is made of G-cell considered as one point and edges that represent the sides here. So, and at that point, this explains the two steps of the routing. First, the global routing on the generic grid, on the G-cell grid, then the detailed routing, which finishes it at the level of the routing. Here is represented the global routing grid in green, with the node, each node is a G-cell here, and the edge connecting them with their capacity. As I said, the capacity of an edge is the number of tracks that you can pass through that edge. For example, here it's 10. But it is too abstracted a model, because it assumes that if you can pass 10 tracks on the edge, you can also pass them all around the G-cell, which is not true. The G-cells contain standard cells that you have to connect to their connectors, and inside you can also have doglegs, turns, and whatever is needed to achieve the detailed routing. So the G-cells are not as transparent as the edge seems to indicate. So to modelize that congestion, the internal congestion of a G-cell, we artificially decrease the capacity of the edges. This explains the two Coriolis parameters, which are ketana.htrace reserved local or vtrace reserved local. It's quantities that we subtract from the edge. So obviously, it will make the work of the global routing more difficult, but is the one of the detailed router. So it's a trade-off. And it's a trade-off that you may have to change for each design. Maybe in the future, I can make the router better, so it can more smartly guess itself that number. But for now, you have to do it yourself. After presenting you the basic step of place and route, let's have a look at the design flow as a whole. And we will start with the symbolic version of the design flow. In the next figure, I will try to respect a color code, which are blue for components that comes from Coriolis, green for the one that comes from Alliance, and red for the one that are third party, not done at Lipsix. And lastly, what is under a light red background is covered by NDA, which means the part that you cannot share with anyone. So, the symbolic flow starts with an RTL description, register transfer logic, which can be written in VHDL, Verilog, or RTL-IL. It comes itself from an HDL language, meaning hardware description language. There are two kinds of hardware description language, like NMigen, which is Python based and may be more suited for people with an electronic background, while Chisel or Spinal HDL may be more suited for people with computer science background. The first step of the toolchain is to perform the logical synthesis, which break the RTL description into a gate-level netlist, which is also expressed in Verilog or VHDL. At this point, you can also perform a validation with GHDL or other tool. In fact, you perform a resimulation. That if you have simulation pattern that you did apply on your RTL description, and then you can reapply them all the same to the netlist to see that, check that the logical synthesis did really make the same design. It is not perfect because you need a complete coverage, which is impossible to achieve, but yet it is a good verification. Then we have the steps we just discussed, that is the place and route with the physical synthesis, which will give you a symbolic layout that you can validate. This will be detailed in further slides. And after that, you can still share the symbolic layout. But to send it to the Foundry, you need to transform it into a real layout by targeting one technological node, which is done with the S2R tool, which contains translation rule, which basically make the scaling, and then you get the GDS. That GDS can also be checked with K-Layout or any commercial tool. The real design flow is somewhat shorter. It starts the same as the symbolic flow, but the logical synthesis and the physical synthesis must use a cell library which is proprietary, or at least non-publishable. Same goes for the generated layout, which is GDS, and which is covered by the NDA, so cannot be published. And as there is no real-world, or at least real layer verification tool, we cannot verify it with free tools, but you still have the possibility to check them with commercial tools, of course. In the last year, we have seen an interesting trend in the sense that Foundry started to release some design kits without NDA, like the Skywater 130 nanometer, which is a very interesting development and that we keep a close eye on. Now, let's focus on the logical synthesis stage. It is needed because it makes use of a lot of files of different formats, and you will see them when you run the design flow. So you must understand what they are and where they come from. So I have already spoken of the VHDL and Verilog file, but you may also see RTL, EL, or BLIF file. BLIF file is in fact the real output of YOSYS. YOSYS doesn't directly generate VST file. It generates BLIF file, which is a kind of netlist file, but an older format. This format we have to translate using the BLIF to VST program. VST itself is a kind of restricted VHDL format for netlist only. It is a format which is particular to Alliance, but compatible with VHDL, basically. All that transformation process is taken care of through the makefiles. That is, we have rules that automatically perform the various translation. But still, you will see the resulting file, so you may understand why they are here. Now, the physical part of the flow. The place and route is not done through makefile rules, but through a single Python script. This is the script you will have to modify to achieve your place and route and to achieve a correct design. So what does this script do? It starts with the input netlist, which is in VST format, the one we just saw about. So this is design.vst, meaning that design is the design you want to realize. So what does that script do? First, it builds a fixed floor plan. That is, from the design, which is only the core of your ASIC, it will build a complete chip along with I/O pads. Then it will perform high fan-out net synthesis if required or if enabled. Then build the clock tree trunk, meaning the H tree. Then place the standard cell around the clock tree trunk. Finally, achieve the clock tree by connecting the individual DFF to the leaves of the clock tree. Then perform the global route. Perform diode insertion if required. And finally, perform the detailed routing. The output is design CTS-R because the netlist is changed. By inserting the clock tree, which is mean here CTS, we tell that the netlist has been changed. So we don't want to override the initial one. Then we have the netlist at the chip level and the API file if we are running in symbolic mode, or directly the GDS file if we are running in real mode. You may also notice that the do-design script make in fact a lot of things which are done either in C++ or Python. This is highly integrated and you will only see the Python interface, but below that you have a mix of Python and C++ scripts. Of course, you will get a template for this file, because for each design you only need to modify a few lines. As we automatically create the top-level hierarchy of the chip from the core, this hierarchy is fixed. So here is a small schematic of the hierarchy. First, the legend. The enclosing box is the cell, which is the model, and inside that model you have instances that themselves refer to other cells. This is the way we describe the hierarchy in this schematic. So on the left-hand side you have the layout, and on the right-hand side you have the associated hierarchy. So we start by what you supply, which is the core. The black part is the core, and this is the netlist that you did supply. Around that core, we wrap the core inside a Corona intermediate level of hierarchy, which is as one instance, which is called core, always, and this level is also called Corona. It's an intermediate level inside in the layout between the I/O pads and the core. It is some kind of adapter. There are technical reasons to do like that, but I won't explain it there because it's too complex for these lessons. So, wrapped around the Corona, we have the final chip level, which contains all the I/O pads, here, I/O1, I/O2, and so on. Those are the pads which are around the chip, and the Corona, which is at the center. So you will see all those netlists appear in your directory. So don't be alarmed, it is perfectly normal. Finally, let's talk a little about the validation step. What are the main validation when making an ASIC? The first one, starting from the layout here, is to perform a design rule checking. The design rule checking will verify that all the rules for drawing your layout are verified. So the fabrication will go well. It means that it is not, the design is valid and will return something which can be fabricated. The second verification is to check that the layout is indeed the design that you wanted to do. To do so, we need an extractor which will read the layout and rebuild a netlist from the layout. And then we can compare the original netlist at the specification with the extracted one coming from the layout through an LVS, layout versus schematic, or in our case, layout versus extracted, to see that we really have the design we want. Those are the two first basic steps. And then we have also the timing analysis. Not only do we want to check that the netlist matches, but also that there is no timing problem inside the design. We perform a second extraction here, which gives us a netlist but with timings, and then we run through a static timing analyzer. And we can see if there are old violation, long chain, and so on. Unfortunately, to perform those steps, we still need many information that are kept in their NDA. So maybe you will not be able to perform that step correctly. Here are the references of the main tools I did build the design flow upon. It is not complete, but it is the most important ones. So we have, of course, IOSIS, Alliance, Coriolis, the Alliance Check Toolkit, K-Layout, and FlexLib. FlexLib is a library to perform designs. We will see that after. And finally, the most fun part, having a demo. We will go through the basic step to build an ASIC with the Coriolis design flow, starting by setting up the working directory, customizing the script and makefile, running it, and seeing how to tune your ASIC to get the best result or to make it work. And finally, some nice feature on how to see what you are doing. After introducing you to the basic of making an ASIC, it is time to start the demonstration. I assume in this demonstration that all the tools are already installed in your system. That is IOSIS, Alliance, Coriolis, and Alliance Check Toolkit. The example I will show is already present inside Alliance Check Toolkit. So, first, let's create a directory into which we will work. We change into it. We need to create a symbolic link to the MK directory of Alliance Check Toolkit into this directory. This link will hold the default rule for the makefile. So here we are. The link is ready. Then we copy the file from the example directory. Same as before. we copy from the CMOS 45 variant of the example, which is a symbolic technology. So we copy the top level makefile. We can then copy the configuration file for Coriolis. This is a directory, so we make a recursive copy. Then the RTL description of the design we want to use. In this case, it's in Verilog. And finally, the doDesign script. Here we are. We have all the relevant files needed to run our example. But before we do that, we can have a look at the various files for the example. The configuration file of Coriolis are put inside the Coriolis 2 directory. Let's see what it contains. It contains the classical init.py file, which tells Python that the Coriolis directory itself is a module and it can be imported. Then we have the setting.py file here. The most important line in this file is this one. This line, this import, tells Coriolis to use the CMOS 45 symbolic technology. CMOS 45 symbolic technology is a symbolic technology aimed to be used with FreePDK 45, hence the name. Then we have this line, which tells Coriolis which signals should be matched as clock, or should recognized as clock. It is a regular expression pattern. So every signal matching those patterns will be understood as clock. The two last lines set up the library, the cell libraries. The first one is the standard cell library, holding the classical cells, meaning NAND, NOR, XOR, and so on. The second one, NIOLib, is the library dedicated to the I/O pads, which can be less portable than the others. So these are the two libraries. Next, we can have a look at the makefile itself. The makefile contains all the information to run the scripts. So at first, we said that we want to use the Iosis logical synthesis step. Then that for physical synthesis, we want to use Coriolis. For technology, we want to use CMOS 45. This is a duplicate from the technology of setting.py. And it should be the same. Otherwise, you will run into trouble. We don't want to work in debug mode, of course. Then we have the netlist part. This list is just the list of VST files that may be generated. The first one must be the core. It must match the Verilog file. It is the same without the extension. And it must be the first, because it is the core, by convention. Then, we include all the rules from the MK directory. Here you see ./mk. So, all the rules are supplied. Not all the rules, unfortunately. The two following rules must be included directly in the file, and eventually they will make their way inside the designflow.mk, but for now they are not there. and they govern the running of doDesign. Is to trigger it's the rules that manage to run doDesign. And finally here, there is a bunch of shortcuts for the rules that allows to run each stage separately. Blyth will just run Yosys, because Blyth file is the output of Yosys. VST is also the output of Yosys, but translated into the Alliance VHDL format, the .vst. Then we have layout, which triggers the place and route stage. And finally, LVX, which triggers the layout versus extracted verification. Druck doesn't work yet. We need to configure Druck to work properly with this technology. So don't try to execute Druck. It will work, but give you errors. So here are the main file. And finally, let's have a look at doDesign. We will come back to it later. But the one more important line is this one. For a standalone run, you can run doDesign standalone directly from the command line. And in this case, this line triggers the loading of the setting.py file. So Coriolis environment would be set up, but that would not be enough. You will need to set up also some environment variable, which is tedious and prone to error. So this is why there is a makefile which takes care of all the initialization of all the environment variable. But if you want and if you know what you are doing, you can do it standalone. The script the Python script must contain at least one function, which is script main, and this function will be executed by Coriolis. Coriolis will specifically look for that function. If it's missing, it will do nothing. Maybe complain. And finally, if you want to execute standalone, you need also to add this small piece of code with just execute script main when the script is run standalone. This is classic Python strategy. We are now ready to proceed to the logical synthesis step. This is quite simple. Just type make VST. Then Yosys run and the Blyth to VST script. We now have the VST file. The VST file is the netlist format, which is VHDL based and which is accepted by Alliance and Coriolis. As we may want to run the place and route stage multiple times, we can back up those VST files. So here we go. And copy the VST file and the Blyth file into ref_VST. This way, we can run the place and route multiple times with deterministic results, meaning that we are sure to start from the exact same state. The next step is the place and route, or physical synthesis. It is also quite easy, just type make layout. For a first trial, we use the text mode. It is slightly faster and much lighter in memory. We see here the placer doing its job. In this small example, it is quite fast. Then the global router here, and finally the detailed routing. Here we are finished and our layout is ready. We can see it if we check in the directory. The epi file has appeared. Epi file for Alliance Physical is the layout format for symbolic layout. So we have our symbolic layout. The last step is to perform some checking. For now, we can only perform LVX, so quite easy also, make LVX. And you see that, of course, its netlist are identical. Make LVX perform two operations, which is the first one, the extractor, known as Cougar, reads the layout and regenerates a netlist in a slightly different format, which is AL, Alliance Layout. No, sorry, Alliance Logical. And then it's compared with the VST file, which is the original one. And we see that terminals are OK, instances are OK, and connections are OK. So the two netlists are identical. We can see the resulting layout with make CGT. Here. You can use the library manager here with Control M and look at what's present. The end result is chip_r. So we want to load the VST and the AP, the logical view and the physical view both. They will be combined inside Coriolis and load. Here we are. We have our layout. So that's the first way, that's the automated way of getting the layout. After running in text mode, we can also run in graphical mode for debugging purpose or pedagogical purpose. But first, we need to reset the design. This is done by doing make clean. The design has been reset. To avoid to rerun IOSIS, we can just copy back the file in ref_VST. But first, I will also enable the breakpoints inside toDesign to perform a step-by-step run. So I look at toDesign and I uncomment the breakpoint level. This will make the script stop at some desired points. So we run make CGT, which start a blank viewer, and then we can load the Python script. Here, do design. Do not put the extension, just do design. So you see, we reach the first breakpoint, which is right after the creation of the chip and the corona level, and also the basics of the clock tree. What you see here is the buffers that will be used to create the clock tree. So now here we are. Now the trunk of the clock tree has been created. You see the wires. There are two clock trees, one for the clock and the other for the reset signal. This explains why the lines are doubled. This is not because you're drawing too much. All the wires are duplicated. So now we can run the placer. What you see here is the placer at work based on the SymPL algorithm. And this is the second placement that you see. The one which is uneven and which at the end came even. So you see it slowly smooths things until it reaches a less than 10% difference. Here you see the end result of the placement, but without the filler cells put in. This is why you see a lot of free space. Lot, not so much, but you see free space. Then the free space is filled and the power lines are drawn. Now we are ready for global, then detailed routing. In order to follow better the process, I will outline one net. So I will use the inspector, the controller, sorry. So here is the controller. And I will select one net. So here, I think a good candidate will see. Choose to select one net. This one has nothing, but see them. We'll try to see nice one. For example, no, this one. So I will select it. But it's not. Zut. I lose it. I did lose it. Okay, this one. 606. Here we are. And we can make a zoom on it. So this is the fly line that indicates that something must be connected. Then we perform the global routing. Okay. Global routing has been performed here. The global routing is based on a Dijkstra algorithm with ripup and reroute. And here you see the 3 steps of ripup and reroutes. First time it did route 1319 nets, then 5, then 5. And it stops when nothing is needed to ripup. So this is very classical algorithm. So the wires are also expressed in terms of global routing. They are not completely finished, in fact. You can also see at this level, we can look at the G cells. They can be visualized if I can grab the handle. Sorry. Here, I will just make them more visible by suppressing everything but the G cells. So here are the G cells. And we can also see the edges. So this is the edges for the global routing. If we go a little bit deeper, you also see that you can visualize the load of each edge. I will suppress the selection so we can better see the edge. Here, it's clearer. So you see, for example, that we are 10 on 10. We have 10 tracks, so the edge is white. There is a scaling of color, the color scaling, which is a heat scaling. The white, the closer you get to white, the more saturated you are. In fact, white is completely saturated. If we go back, you can have an impression about how dense your design is. You see that you are dense by here and less dense otherwise. The fact that you can see or not see the edges depend on your zoom level, because at a certain scale it just disappears. For example, here I just zoomed again and unzoomed again and everything disappears. So let's zoom back and go back to our net. And I will restore the normal display. So I display everything but the grid. And I remove the G cell and the edges. So now we can proceed to the detailed routing step. Okay, here we go. So now the net is fully routed, and you see that the routing has succeeded, as the little window says to you. So you see that it has moved it has moved the wire, some of the wire, into the metal 4 and metal 5, because the edges were overloaded or highly loaded, so the router did estimate that it was better for him to go up. If we get the full results here, and finally we get back to the complete chip. So this is the visual demonstration. What we have seen until now is scripts that works. But what happens if something is badly written or a parameter is wrong? I will now show you a selected set of potential errors. So we will edit design.py, remove the step-by-step mode, and first we will increase the core size without changing the chip size. So the core will be too big for the chip. What will happen? To rerun in the same condition as before, I will perform make clean, copy the backuped VST file back, and run make CGT so we can see what happened. Then I call do design, and we pop up an error. And the error is the core is too wide to fit into the corona. So this is the kind of error you get if your core is too big. So you can solve it by either shrinking the core, if it's possible, or expanding the whole chip size. Now, secondly, we'll make another kind of error. I restore the right size for the core, but I will slightly shrink the chip itself in horizontal direction. I remove 100 lambda on the width of the chip. What happens now? This time, we get another error telling us that the chip is not wide enough to put all the pads on the north side. If you get back to the previous presentation, to the previous part of the presentation, you will see that the north pads are side by side. So removing any length from the width of the chip causes an error. So this is the other kind of error. we will now look at the router's parameters. So, if I also do design to change the number of reserved tracks for the local routing and put them all to 0, for example, and restart my script, what will happen? So the placement runs. I did restore the right parameters. So we have to wait just a little bit until it reaches the global routing. Okay, now you see that the global routing here, okay, I will wait just a little. First observation, here, the global routing didn't have to make any rip-up. Everything went fine at the first try. It means that it has a lot of space. And this is expected because I didn't put any local constraint on the G cell. I said that every G cell can go through as they want. They have all the capacity, they have the full capacity of all the edges. So obviously, this is much more easier for the global router. But on the other hand, what we see at the end of the routing is that we see the routing did not complete unrouted segments. That is, the routing has failed because it didn't have enough local capacities in the G cells. And you have a report here, and what you should look is there, that it says that you have 12 segments that are unrouted. The number here is the number of routed segments plus the number of unrouted segments. You have also the same computation, but for the total wire length, and also statistics about how many horizontals were unrouted, 8, and how many verticals were unrouted, 4. So that explains why we need those parameters. So I will restore them to a much higher value, for example. Not the right one, but higher still. So I will put 3 here and 3 here. We'll start to reserve tracks. And here we go again. So we wait for the placer to work. Okay. Maybe I should have chosen something faster. Okay, not enough. See that we got the same error as before. So we must increase. This may be your work to increase the parameters until it works, but not too much. Because otherwise, if you increase them too much, you will make the global routing too difficult. Here, if I go up to 10, I will make the global routing very difficult, but very easy for the detail one. So, Another try. In the future, I hope to enhance the router so it can guess better those parameters and ultimately guess them fully automatically. But for now, they are just manually set up. So here we go again. And now you see that the global router has a lot of problems. You see that this time it took him 10 iterations and to not even succeed. At the end, it stopped at 9 iterations because there is a limit. I put a hard limit to 10 iterations. It can be changed, of course, but for now, for this example, it's at 10. So it didn't succeed. And it gives you an histogram of the saturated edge. And the funny thing is that even in that condition, it didn't finish the detailed routing. So the place and route is still quite sensitive settings. So you will have to try to adjust your parameters. So here we are. Thank you for attending this presentation. I hope it will be useful to you, and have a nice day.